Great to be here. Thank you, Dan. Let me go ahead and share my screen. All right. Is it working okay?
I see
All
it.
right, perfect. So great to be here. We've been at Interconnect for several years now. I think it's becoming an incredibly important conference as compute performance moves from computing to interconnect as the main bottleneck. So let's jump in here. If you look at what's happening in industry, everyone's focused on AI, specifically training and inference. What's interesting about training and inference is they're multi-phase and they have really different computational properties. What we're showing here is a roofline plot. And you can see that for training, you're really in a compute-bound workload. This means that applying more compute is generally going to give you performance improvements. Inference really has two phases, and you've seen a lot of companies splitting between prefill and decode. Prefill is compute bound and decode is memory bound. And so what I'm excited to tell you guys about today is our passage technology accelerates all three of these workloads and phases of workloads, training and inference, prefill, and decode. So I'll give you the headline numbers first. With Photonic Interconnect enabled by Passage, you can get a 3x reduction into time to train AI models. We'll talk about the details of that. We won Industry Best Paper Award last year at this conference for that work. And then, new work from the team was presented today, or will be presented today, on what Photonic Interconnect does to inference. 3x reduction in time to first token for inference prefill, and a 2x faster inference decode. So there's a lot on the table with moving to photonics for these platforms. First, let's talk about training. What we're going to do here is we're going to compare four 144 GPU racks that are networked with copper in the rack and optical pluggables between the racks. We'll take that as the baseline. So 4 by 144 GPUs. And then we're going to compare that to a full optical scale-up network enabled by our Passage Photonic Interconnect. Exact same bandwidth, same number of GPUs, but we've gone from a 144 scale-up domain with copper to a 512 scale-up domain with photonics. You're at about 2x, 1 over 0.6. And if we increase the bandwidth up to 32 terabits from 14.4, an NVLink type baseline, now you're almost tripling the training performance. So you're finishing a model training run in 1/3 of the time. You can see the paper there on the bottom from one of our team members, published in IEEE Micro. Check it out. Let's look at what Photonic Interconnect does to prefill. Now it's context length dependent, but most workloads, when you're using an AI model to do real work, are around 130,000 tokens for the context length. And what happens here is as you increase the context length, we're getting an improvement in time to first token. So this is going to make a big difference in what it feels like to use an AI model. You're going to be getting answers back quicker. And then on the decode side, so Passage really lowers inter-token latency, ITL. So you've got 2 times faster decode versus copper scale-up. And this is across short and long context lengths. So really exciting results. I think these are things that will principally motivate the transition to photonics for scale-up networking. So scale-up networking is very exciting, and the core idea is having more GPUs, more XPUs in a single computational domain with ultra-high bandwidth interconnect at very low latency, thereby enabling a single giant computer. But to get there, we're going to need a lot of lasers, and we're going to need a lot of optical fibers. The whole industry is excited about HBM, and it's an incredible shortage at this point. Companies like Samsung, Micron, SK Hynix doing very well in the shortage. I've got good news and bad news. Lasers and optical fibers are the next HBM. At Lightmatter, we solve these two supply chain challenges with our technologies, bidirectional optical links and DLSP. And let's jump into those. So what's BiDi? BiDi is taking what's normally two optical fibers and merging them into one. In one fiber, you have the transmit and receive paths included. Now, if we look at how photonics has been viewed historically, it's typically viewed as a dongle for electrical SerDes. You have your SerDes on your chip, an electrical signal gets driven to the optics, and the optics just deals with it. We've gone from 56 gig to 112 to 224, and 448 chips are just starting to show up in labs at certain companies. With the OCI MSA that was just announced, photonics is finally in the driver's seat. These electrical devices are now going to be designed to be optimal for photonics. And the big story with OCI MSA is DWDM, which means multiple colors per fiber, and bidirectional. Generation 1 is packing 200 gigabit per second per fiber, matching a 200 gig SerDes rate. Gen 2, 400 gig, Gen 3, 800, and Gen 4, 1600. One of the fun things at Lightmatter is we have Gen 2 and Gen 4 silicon already in our validation labs today with hundreds of platforms running. So let's talk about the physics of BiDi. What's going on with BiDi is we're taking banks of colors. In this case, we're showing 16 total colors. 8 of them are used for transmit, 8 for receive, and they're packed into a single optical fiber. It's single mode fiber, the standard sort of common optical fiber there, but we're packing them in a single fiber, transmit and receive passing each other. And the chip, the photonic integrated circuit, has to separate these directions on its side. You also need incredible lasers to power this kind of technology. Earlier this year, we announced our Passage L20, a universal near package optics engine. It'll come in an OpenCPX form factor, XPO, and chip on board. 6.4 terabit per second, featuring our BiDi technology, 2 lambda BiDi. So 1 color out, 1 color in, 224 gig each direction, 400 gig per fiber. And it's available in the NVIDIA NVLink Fusion ecosystem. So go check out Passage L20 and give us a call. On BiDi, let's talk about a 512 XPU scale-up cluster. What does it buy you? And we're talking about the shortage earlier. With 512 XPUs, we're saving 150 miles of optical fiber, 20,000 fewer connectors. So you have 20,000 less points for the technicians to plug in when they're setting up a 512 GPU scale-up domain. And you're saving 16% on the overall network cost. This is an absolute no-brainer. BiDi technology pays for itself, and Passage L20 is the first to market with the technology. So that's BiDi. We're going to be able to build gigawatt AI data centers using half the optical fiber. Now, VLSP, very large-scale photonics. Here I'm trying to draw a parallel with what happened with transistors in the 60s. They went from discrete components to integrated circuits, and Intel famously did a lot of the work that was driving from the discrete transistor to integrated circuits. Let's do the same thing to lasers. Lasers are going to be powering near package optics, co-package optics, and Lightmatter's technology, photonic interposer. We do all three, near package, co-package, and photonic interposer, and those involve external light sources. The form factor looks like this module on the bottom right with the blue handle. And what's interesting is with traditional technologies, we're already at a spot where you have so much laser light going into the fiber, 400 milliwatts, that the fiber undergoes fusion. If there's any contamination, 500 milliwatts is really the melting point. To power a 100 terabit per second switch, you need 16 modules. And by 2030, 2032, switches will be at 800 terabits, and you will need 128 of these modules. There's no Moore's law left for scaling laser optical power. So just imagine 800 terabits needs 128 of these modules. That's not a future that we're excited about, and I don't think data center operators are either. We talked about the OCI MSA. So lasers are moving to multicolor. In the OCI MSA, the micro ring modulator, the modulation technology that Lightmatter uses, is defined as the default. Now, one of the challenges with lasers, conventional laser diodes today, is they vary a lot in optical frequency. The color of the light is varying in time. Not only that, but the intensity of the light is varying in time. And you have to have these micro ring modulators following the laser lines, both in amplitude and in frequency. This results in dropped links and increased link insertion loss. This is a central challenge that needs to be solved. And here's how we've done it. On the left, a discrete indium phosphide laser. They're really a bag of parts. You take the lasers and glue them on a substrate, image the light with lenses and isolators through the air, and get those onto an optical fiber. With Guide, what we've done is in this chip, 128 lasers in a single die. The packaging looks like conventional CMOS packaging, flip chip, 128 lasers per die, from a bag of parts to a chip. So let's zoom in a little bit more here, and let's look at the ELSFP form factor and see what we can do with Guide. 128 lasers per chip today. We're moving to 512. zero point 0.1 fit, 0.25 dB power accuracy. That means the power is not fluctuating. Today, we can go from 1 to 64 colors and beyond. We build these in 300 millimeter CMOS foundries. We talked about the laser shortage. This is going to help significantly. What's going on with normal indium phosphide lasers is you have indium phosphide foundries. They process small wafers, and they're building those little foundries as fast as they can. With Guide, we're building these lasers in 300 millimeter CMOS foundries. We have new capacity that we're bringing to the world, and we have the most power accurate and frequency accurate and stable lasers in the world. So at Light Matter, we have photonics in every form, from near package optics with an optical engine near the GPU or switch to CPO with the photonics inside the package, our partners at TSMC, Global Foundries, and others, and photonic interposer. We're the only company in the world with the 3D stack of photonics and GPUs or switches. All of that in silicon today. So come visit us and you can see our validation platforms, Guide 1, EVK50, 100, and Passage M1000 Photonic Interposer EVK. All of these are in our validation platforms and with customers and hyperscalers today. One last thing I want to call out, in order to get photonic technology to market, we have to define what the rack is going to look like. We recently announced our vision white paper with 19 collaborators, really the world's leaders in ODMs for building racks for AI data centers. And we're defining what the XPU tray, the switch tray, fiber routing, rack design, and everything else is going to look like through OCP. All right, and that's all I've got.
That's all, huh? That's not enough. Uh, Let me just ask a quick question. So on Guide, you've got 128 lasers on a die, 300 millimeter wafers, CMOS SOI. Um, but lasers don't really grow on silicon. So how are you doing that?
Yeah, there's a foundry technology that we didn't invent that a number of foundries use at this point, where an indium phosphide wafer is bonded into the back end of line of a CMOS
I
300
see.
millimeter wafer.
Okay,
There's no indium phosphide fab involved, and so that's a technology that multiple foundries have.
great. Thank you, Nick. Excited. Thank you for sponsoring for a number of years, just a stalwart and an incredibly innovative company. So thank you for sponsoring, for speaking, Nick. We now have a 10-minute break, and there will be music. And take a break, and we'll be back in 10 minutes for the rest of Hot Interconnects.
All right, thanks, Dan.
Thank you, Nick.